In this video, we're going to continue finding values from the property table, but this time we're going to cover a new phase, which is saturated mixture. Okay, so let's recall the 5 phases of pure substances we have from compressed liquid to superheated vapor. Okay, and this diagram represents, this is a TV diagram that represents the process. This is the boiling process at constant pressure. All right. And of course, you have to include the bell curve just to make it easier for us to see the change in phase. Okay. Now, in the previous video, you have covered saturated liquid. So anything, if it's saturated liquid, this is where it should be, and you can find values based on this phase. In the previous video, you have tried to find values such as pressure and specific volume, okay, which is on this axis. We also covered saturated vapor. So a liquid that is completely vaporized will be saturated vapor. We can also find values of specific volume here. Okay, now in this video, we're going to do the middle phase, which is saturated liquid vapor mixture, or simply saturated mixture. Okay, and this phase is along the horizontal line. So it's a little bit more complicated because it doesn't just cover one point on the graph, but it covers the whole line. So there's a range of values that is possible for saturated mixture. Okay, and please remember that this whole theory can be applied to both water and refrigerant, at least in the context of your studies. Okay, so to make it simpler for you, now we're just going to cover water first. Okay, and the same thing can be applied to refrigerant, except that you use a different set of tables. Okay, so saturated liquid vapor mixture. The first thing for you to know is this new property or new number called quality. Okay, the name is quality, is written as X, the symbol is X, and it means that it's basically the ratio of the vapor mass, M here is mass, divided by the total mass. Okay, so if you look at the definition, it's actually just how much vapor inside the entire system. Okay, in other words, it is the quality or the percentage of gas inside the mixture. Simple words. Okay, how much gas is inside the mixture? That is quality. Okay, so total mass here is, of course, the total mass of liquid plus mass of vapor. Simple as that. We're going to write M liquid as MF to be consistent with the property table. And M vapor is Mg. Okay, so here is Mg over M total. In a mixture, temperature and pressure are dependent properties. One value immediately determines the other. So if you know a temperature, you will automatically get the pressure. If you know the pressure, you'll automatically get the temperature. Okay. Now, I think I've mentioned this before in previous videos. A two-phase system can be treated as homogeneous mixture for convenience. Let's say you have liquid water at the bottom and then vapor water at the top. Okay, this is just steam, right? We can treat it as a homogeneous mixture. So we don't distinguish the two different phases. We treat it as one whole, same thing, which is mixture. All right. Okay, let's work out some equations for saturated mixture. So this is the PV or TV diagram. You have the bell. The mixture is anything that is under the bell. Okay, anything under the bell is a mixture. And typically, there will be a horizontal line at which a mixture is able to exist. All right, because it's happening always at the same temperature or pressure. Okay, first, the equation to get the specific volume of a mixture let's say we are referring to point 1, it's V1 referring to here, this is the V, is equal to Vf plus X VFG. Okay, that's a lot of information. Vf is the volume of the fluid or volume of the saturated liquid state is in the property table plus X is the quality, times VFG. VFG can also be obtained from property table. Remember, VFG is Vg minus Vf. So this is how we get a property value for the mixture. For example, this mixture. Okay, now the unit is meter cube per kg because it's specific volume. VFG, as I mentioned, is Vg minus Vf. And X is the quality, referring to the previous slide, is a mass of vapor over total mass. Okay, but this equation V1 here can also be rearranged and you can solve for X. Sometimes we don't have this, okay, and instead you have to find the quality. So there's only two ways you can find quality, either through this when you have these masses or using this equation, which is from the specific volume. In this case, of course, you have to have all the other values to get X. All right. Now, very important criteria. V1 or V of a mixture is always in between Vf and Vg, which is very clear on the P or TV diagram. This is Vf, this is Vg, and V1 is always in between. It cannot be more than Vg. It cannot be less than Vf. Okay, the same concept of this can be applied to all the other properties in the table. For example, internal energy U, enthalpy H, or entropy S. The same thing can be applied. For example, internal energy can be written as this. U1 equals to UF plus X UFG. X will be the same. Okay, X here and X here will be the same number. And this relation also applies for internal energy. The internal energy of a mixture is always in between UF and UG. Same thing for enthalpy as well. Okay, let's go through this example. A rigid tank contains 10 kilograms of water at 90 degrees. Okay, if 8 kilograms of the water is in the liquid form and the rest is in vapor form, determine the pressure and volume in the tank. So what we know is we have the temperature is 90 degrees, and based on this, okay, let's say you were not told that it's a mixture. It said that 10 kg is the mass of water inside the tank, but 8 kg is in liquid form. That means that there's another 2 kg that is in vapor form. So that is enough to tell you that this is a mixture. Okay, so I have the TV diagram here. Mixture is something in between. We draw the bell, we draw the constant pressure line. Mixture is somewhere in between. This is the information we have. The mass of the gas or vapor is 2 kg and the mass of the liquid form is 8 kg. Stated here, yeah? Okay, so P will be equals to P set. Why? Because at this temperature, of course, it's happening along this constant pressure line, which will be your P set. You can also draw the PV diagram. Okay, you can also draw the PV diagram for your own understanding. So the volume in the tank is related to the specific volume. Okay, remember the mixture fills up the entire tank. So you can find the volume, how much water is inside. That will give you the volume of the tank. So we use this equation because it's a mixture. V equals to Vf plus X Vfg, and X is the ratio. How much vapor inside the entire tank. So that's 2 kg over 10 kg, which is 0.2. That's your value of X. Vf and Vg can be obtained from the property table. Okay, so VFG, remember, is Vg minus Vf. plug in the values and you should get this. Please pause the video if you uh, want to slow down and calculate this. Okay, so here is not the final answer yet. This is specific volume. So you have to find the volume of the tank or the volume in the tank. Therefore, you have to multiply by the mass. Right? So volume is 10 kg times the specific volume and it will be 4.727 meter cube. Right, what you've learned so far in this video and in the previous videos, you've covered table A4 and A5. Okay, you've understood how to find T when you have P set, how to find P when you have T set, and how to get the specific volume values, VF, VG, and VFG. Alright, and next, you have also learned how to find the specific volume for saturated mixture phase. Okay, so related to that, you have also learned about the quality when you have a mixture, which is X. In the next video, we are going to cover the two phases which we have not covered yet, which are superheated vapor and compressed liquid.